Tonight, you and I are setting up my telescope to answer a quiet question: why almost everything spins, planets, stars, galaxies. Get comfortable, close your eyes, and just listen, because once I show you this pattern, the whole cosmos feels calmer. Chapter 1: Our universe rejects stillness. When I look through my lens, nearly every object I can name is moving. The moon drifts slowly across a background of stars. Even those background stars are moving, just way too slowly for a single human lifetime to notice. Constellations are just temporary sketches. They only seem permanent because cosmic change happens on massive time scales. Even the dark space between stars isn't frozen. It's filled with thin gas, cosmic dust, and light traveling for millions of years. Down here on Earth, we learn rules about motion that work daily, but completely mislead our astrophysics. Roll a ball across the floor, it stops. Spin a top, it wobbles, loses its speed, and falls. Our home planet is packed with heavy friction, air resistance, constant forces, tiny vibrations, and sounds. All that organized movement turns straight into heat, which just bleeds away into the air around us. It makes us assume that rest is the natural end state, and motion always needs an engine pushing it. Physics shows a different default. Without outside forces, an object continues doing exactly what it is doing. If it's moving, it keeps moving. If it rotates, it keeps rotating forever. This isn't just poetry. It is hard data from the observatory. The reason a rolling ball stops in your bedroom isn't because motion naturally dies. The real reason is your room is packed with things that steal motion away. The floor pulls the ball, air tugs at it. Microscopic friction inside the floor simply converts organized speed into messy, random vibrations. That energy and momentum are not destroyed. They simply scatter into the surrounding space as forms that no longer look like motion. Deep space isn't perfectly empty, but it is incredibly gentle compared to your living room. Out between planets and stars, I see plasma, faint dust, scattered atoms, and streams of radiation. But the density is so low that the breaking effects we expect on Earth take billions of years to matter. A satellite keeps right on orbiting because almost nothing up there can slow it down. A planet keeps spinning because no solid ground scrapes beneath it, and there's barely any thick atmosphere to act like a brake. A rotating star maintains its spin for eons. It has no solid surface grinding against a rough environment, unlike the objects we play with in our daily lives. Even the concept of absolute stillness starts fading the closer I look. Drop a star chart on the desk, looks perfectly still. Atoms are vibrating inside. At room temperature, those vibrations never quit. In the air around my telescope, molecules dart everywhere. Inside my coffee mug, molecules constantly rearrange. What we call resting is just an average. The physical object sits totally quiet to our eyes, even though it is bursting with invisible microscopic motion. Shrink down to the quantum scale, and perfect classical stillness gets much trickier. Quantum systems are never just tiny beads frozen with exact positions and perfect speeds in one spot. We define them by uncertain states and lowest energy configurations that retain what my physics colleagues call zero-point motion. The math changes per system, but the grand theme stays wonderfully consistent. Mother Nature simply refuses to let every degree of freedom drop to absolute zero motion, unlike the old classical models thought. Modern astrophysics describes empty space as fields, and those fields constantly ripple and fluctuate. This doesn't mean deep space is just random chaos. It just means absolute cosmic stillness was never the true baseline reality. So let's figure this out together. Why does the whole universe spin? It is simple. Motion is incredibly common and hard to erase. To force motion into stillness, you have to build a path for momentum to escape the system. Down on Earth, those paths are everywhere. In deep space, they are incredibly rare. That fact alone makes long-lived celestial motion totally normal. But our universe doesn't just wander randomly. It moves with brilliant organization. Planets spin, moons orbit gracefully. Huge disks trace circles, stars rotate tightly. Entire galaxies turn as millions of suns orbit inside. The beautiful persistence of this cosmic motion comes directly from physics laws, especially the conservation of angular momentum. Angular momentum drives every spin and orbit. keep looking up with me, we'll spot it. Looking through the telescope, a planet circling its star carries angular momentum. Even if that world doesn't spin on its axis, in a closed system, total angular momentum is conserved. In our cosmic models, this momentum shifts from one body to another. It gets redistributed across the dark void, but it never simply vanishes. This is why cosmic rotation is so incredibly hard to erase. To slow its spin, a solar system must pass that momentum to something else. Tonight, you and I will see that stillness is not a destination the universe automatically seeks. Complete stillness is rare. It only happens when cosmic interactions have had enough time and endless opportunities to gently carry that motion away. Down here on Earth, a spinning wheel slows quickly. It just hands its momentum over to the air, the axle, the ground, and the quiet vibrations of its own material. Out in the void, a wandering planet has far fewer partners to catch that momentum. Over deep time, certain processes still slow these worlds down, but they must work through very specific physical mechanisms. For example, we observe tidal forces slowly trading angular momentum between spin and orbit. Drifting through thin stellar gas creates gentle drag. Powerful magnetic fields can also tie rotating matter to quiet winds of charged particles. As scientists, we know this principle well. Motion shifts because unseen forces and interactions pull the strings, not because the cosmos prefers deep rest. Let's step deeper into the dark together. Where did all this beautiful, chaotic motion actually come from in the very beginning? The ancient universe was intensely hot, dense, and packed with particles and glowing radiation in constant, restless interaction. In that fiery state, movement is simply unavoidable. Temperature itself is just a measurement of endless microscopic motion. As our vast universe expanded and cooled, that motion never faded. It merely scattered. Those chaotic particle dances became the starting conditions for the massive cosmic structures I observe today. What my colleagues and I see through our lenses matches the lab theories perfectly. Tiny cosmic ripples slowly blossomed into the vast structures we map tonight. When gravity amplified tiny shifts in density, stellar matter naturally drifted toward regions that were already slightly heavier. We might picture this cosmic inflow as perfectly straight, like bright arrows all aiming inward at a quiet center. But in the deep sky, perfect alignment is impossible. Stardust drifts in from every possible angle, arriving with gentle sideways drifts and beautifully random deviations. Gravity never erases those sideways drifts. Instead, it smoothly bends their falling trajectories. A tiny sideways drift curves through space, and that curve becomes a steady orbit. As matter flows inward, I watch how those delicate motions aren't just preserved. They become vital because the cosmic collapse strongly concentrates them. Picture a massive nebula slowly collapsing to birth a new star. No real gas cloud is perfectly smooth. I always see quiet turbulence and heavy, irregular clumps. Distant supernovas might stir it, yet even without that outside push, internal currents always ripple through it, simply because the stellar cloud carries heat. Every wisp of gas carries its own gentle speed. As gravity drags the nebula inward, those fragments collide. Soft collisions and friction inside the haze slowly dampen out certain chaotic, random movements, especially the motion. That would send stardust crashing through the same exact space in totally opposite directions. Those delicate encounters can soothe the chaos, but they don't simply erase the nebula's grand, spinning angular momentum. If I detect even a faint whisper of rotation in that cloud, the strict laws of conservation ensure that beautiful spin survives. This cosmic process naturally produces a beautifully flattened, rotating disk. Speeds tilted sharply away from the glowing equator are quickly smothered by collisions. Meanwhile, the gentle flow along the flat plane thrives as one coherent, spinning waltz. This disk isn't just a lucky accident. It's a deeply common result of cosmic collapse in a universe where angular momentum is fiercely protected, and where stellar collisions iron out chaotic paths without ever destroying the grand, overall spin. When my telescope catches young stars draped in halos of glowing gas, it perfectly proves this theory. It sets the dark stage where new planets will eventually grow. From these quiet disks, planets are steadily built. Dust grains collide, stick, and gently grow. Giant bodies sweep past smaller fragments, carving deep orbits and clearing dark lanes. Through this ballet, momentum trades hands, but the grand total remains completely untouched. A finished solar system forever carries the spinning memory of its original cosmic disk. A distant planet's day. Its tilt and its orbital path are permanent historical records. They are scars of ancient impacts and gentle gravitational pulls, perfectly written into living motion. Let's remember this tonight. A planet's rotation is literally deep history you and I can measure, and those burning stars follow the exact same logic. I observe young stars spinning intensely because they form from collapsing stardust that was already rich with swirling angular momentum. A blazing star slows down over the eons, but only through strict physical channels, like tying magnetic fields to solar winds or heavy tidal drag in tight binary pairs. Even when a massive star slows, that swirling angular momentum never simply vanishes. That energy bleeds into the deep vacuum or shifts into endless orbits. I've learned firsthand that our universe rarely chooses stillness. It simply obeys physical laws. Even on massive scales, I watch distant galaxies pick up a gentle spin as they mature. Neighboring clusters pull on infant systems, creating massive gravitational tides that set them slowly turning. Collapsing clouds of gas flatten into vast turning disks, and even galactic collisions only reshape that spin without ever destroying it. The mechanics become wonderfully rich and complex. Yet the core truth stands. Motion is inherited, kept alive, and shaped entirely by gravity. That explains the greatest paradox we observe. The sky is violently dynamic, yet perfectly stable. Orbit and spin actually protect matter from a fatal collapse. They fan stardust out into flat plains, stretching time and creating long-lasting cosmic neighborhoods. We don't live in a cosmos of dead stones that suddenly jump. We live among restless matter that occasionally finds a quiet, stable rhythm. As we close this first chapter together, let the simplest truth sink in. Endless motion is everywhere. Absolute stillness is incredibly rare, born only from friction and deep time. Out in the vast, empty dark, motion always survives. And when gravity finally sweeps that matter together, that ancient speed organizes into graceful orbits. Every spin is just the cosmos remembering how it was born. Tonight, I hope you find some quiet comfort in that thought. The endless turning above our telescopes is never rushed. It is steady and certain, like a massive clock that never needs to be wound. Let your breathing slow down with it. Let your long day unwind until your mind feels as peaceful as the silent space between the stars. Chapter 2, the very first push, tiny imperfections just after the Big Bang. Long before I could point a lens at planets or watch a star rotate, the early universe was already rejecting the idea of perfect symmetry. This part of our story is about that gentle drift away from perfection. No dramatic shove or giant cosmic hand, just something beautifully subtle. Microscopic differences planted early, carried through time, and quietly amplified. Under the strict rule of gravity, even the tiniest uneven patch changes everything. Imagine the infant cosmos as incredibly smooth. Across massive distances, early light and matter were painted in an almost perfectly even coat as space expanded everywhere. But if that smoothness was flawless, gravity would have had absolutely no building blocks. A completely uniform void offers no downhill slope for dust to fall into, simply because every single coordinate would be an exact clone of the rest. In that kind of dead cosmos, space might still stretch outward, and hot plasma might jitter on a microscopic level, but you would never get the breathtaking, structured galaxies I observe every single night. Instead, that early dawn held tiny, beautiful flaws. These were not solid lumps of rock, and they certainly were not spinning bodies. They were just the faintest ripples in density and heat from spot to spot. So small the expanse still appeared smooth, but heavy enough that gravity could slowly magnify them. And let me tell you, this isn't just an elegant myth we astronomers invented. It is backed by some of the most exact, hard data ever collected in modern science. We call it the cosmic microwave background, the fading glow wrapping our sky. That old light is the frozen echo of a time when the cosmos finally cleared. When we point our most sensitive instruments at it, we uncover something profound. Its temperature is breathtakingly steady across the sky, but never perfect. You can see subtle textures, faint shifts in warmth as you scan different directions. Those delicate shadows act as a fossil record, marking where ancient pools of primordial plasma varied. It shifted how early light scattered, while gravity sapped the energy of photons struggling out of the deepest valleys in spacetime. You might wonder why texture even exists here. Well, the laws of physics simply refuse to allow perfect, unbroken sameness. Right after birth, the cosmos was violently hot, but heat is never just a feeling. It means frantic microscopic motion and pure, tiny randomness. Inside a boiling plasma, light and matter collide without pause. There is simply no cosmic rulebook forcing every single pocket to freeze into the exact same microscopic shape. Quantum mechanics adds another wonderful layer. We view the entire physical world through fields that naturally jitter and vibrate. And in extreme environments like the early dawn, that restless vibration can never be zeroed out entirely. My colleagues and I still actively debate where those very first jitters came from, but the overall timeline remains firmly agreed upon. Our universe began almost totally flat, scattered with tiny, measurable, mathematical ripples. As the endless void expanded and froze, those subtle ripples lived on. By the time our universe cleared, that ancient signature was frozen into the microwave background. For us astronomers, that map is no simple picture. It's a precise blueprint, revealing the tiny, heavy, and light spots that eventually grew into every star system. Give the cosmos the slightest unevenness, and gravity takes over. The pull of mass needs barely a head start. It works slowly, endlessly. A slightly heavier patch simply tugs on nearby stardust a bit harder than its surroundings. As loose gas drifts in, that heavy spot grows denser and its pull intensifies. This gathering fights the expanding void. It takes eons, but the cycle is unstoppable. A baby universe starts with a mere whisper of texture. Over billions of years, gravity sculpts it into vast cosmic peaks. Back then, regular matter could not just fall freely. Our cosmos was a hot soup, with free electrons and light endlessly colliding in a brilliant fog. Light and matter were locked together, moving like one unified fluid. Whenever gravity tried to squeeze this ocean of light, the heat pushed back, it launched rolling waves instead of collapsing. Those ripples left a permanent mark. Looking through our telescopes today, we see their ghost in how galaxies are scattered. It is a frozen memory of sound echoing through that ancient fire. As expanding space slowly cooled down, it hit a tipping point. Free electrons finally settled onto atoms, calming the chaos. Without those loose charges blocking the way, light broke free. For the first time, deep space became clear. The light released then has been flying ever since. It cooled with expansion, washing over our instruments today as the gentle microwave background. With the blinding light gone, ordinary dust could finally drift downward. The heavy drag of radiation could no longer hold it back. Now space still lacked the spinning, starry worlds we see tonight. But the seeds for those swirling galaxies were quietly taking root, born from the uneven gravity and the slow, graceful drift of ancient dust. A flawless, perfectly balanced inward collapse would mean every heavy spot was an isolated, flawless sphere, pulling matter from all sides in total, perfect harmony. Nature is far too messy. Dense pockets simply bled together. They stretch and warp under nearby gravity. The swirling gas flows were complex, even when density differences were still tiny. As primitive matter sank into these deep, unseen valleys, it never fell in straight lines. Gas drifted sideways, pulled off course because the gravity was lopsided and the incoming rivers were totally misaligned. That sideways pull bent the falling gas into gentle curves, causing shear. Neighboring streams brushed past each other at totally different speeds. That shearing motion brews incredibly complex currents. It stretches and stirs the quiet gas, sparking the very first hints of rotation, long before any flat, spinning disks lit up the dark. As giant structures swelled, the gas rivers rushed faster. Crashing streams sparked massive shockwaves, violently grinding that forward momentum down into raw heat. Hot gas fights back against the cold. It briefly stops the crushing weight, boiling up into a chaotic swirl of ripples and wild storms. But turbulence isn't just chaos. It's the engine that moves energy, folds dust together, and pushes motion deeply through the void. In the dark ages of creation, these storms dictated how gas broke apart, chilled, and finally rested in the bottomless craters gravity was digging. Dark matter deepens this entire mystery. Let's look at this together. While regular dust was trapped by light, dark matter started clumping way earlier. It completely ignores light's glowing embrace. It obeys gravity, forming massive, ghostly halos through slow mergers. These halos act like gigantic, totally invisible cosmic basins. When normal dust finally broke free to sink, it tumbled right into the deep valleys dark matter had already dug. Since these invisible craters aren't perfect spheres and they drink from long threads of gas, the drop is wonderfully lopsided. That lopsided, tumbling dive is exactly what forces everything to start spinning as the eons pass. If I step back far enough, the universe's grand structure simply looks like a vast, glowing web. My deep sky surveys reveal glowing threads of galaxies. Glowing sheets, heavy knots bursting with massive clusters, and terrifyingly empty voids. This web is just the mature shadow of those ancient ripples. It's exactly what you and I should expect when gravity spends billions of years stretching tiny bumps across a dark, expanding universe. Out there in this web, I watch matter stream toward dense nodes. These flows collide and bend. To an astronomer, every single motion holds clues about the early universe's texture and the long, slow pull of gravity that came after. But you and I need to get the timing right. The cosmic microwave glow doesn't show me a sky full of completed galaxies. Instead, I see the very first seeds, just a faint, gentle ripple across an otherwise average sky. The spinning motion we know today shows up later, once those seeds break down and massive structures finally collapse, merge, and settle. What this ancient light gives my instruments is that first texture, the early movements that make all this later spinning perfectly natural. It tells us the cosmos began slightly off balance, and for an astronomer, that tiny imperfection is all it takes to spark a massive cascade of order. I find a quiet beauty in how little was actually needed. The universe didn't need some massive cosmic spin switch flipped on at birth. It just needed an opening state that wasn't perfectly smooth. As long as the rules of gravity and radiation stayed steady while the cosmos expanded and cooled, deep complexity was bound to follow. Tiny shifts appear, currents bend, matter pools into gravity wells that are never perfectly even. Much later, when cooling gas settles into lasting structures, I can see how those ancient, tiny imbalances force the natural turning and orbiting we observe through our telescopes today. The biggest superclusters I mapped tonight started as faint ripples in an empty sea. It proves the cosmos can build endless wonder without demanding a perfect beginning. Tonight, let's just let that idea soften the day. And rest with a calm confidence, knowing the smallest beginnings can still grow into something vast. Chapter 3: The Conservation of Angular Momentum, the hidden rule making cosmic rotation inevitable. If I had to pick one single principle that explains why everything in the night sky spins, it's this exact rule: the conservation of angular momentum. This isn't some mystical force pushing the stars around. To a physicist, it's just a simple bookkeeping rule baked right into the fabric of space. It works just like the conservation of energy or the conservation of linear momentum. When a star system sits entirely alone, safely away from outside pulls, its total angular momentum stays locked. I watch it move from one passing moon to another. It shifts between different kinds of drift and orbit, but that motion can never just vanish. That single truth turns cosmic rotation from a simple curiosity into an expectation. Let's break this down. It helps to separate two things that look alike but act differently. First is spin, like Earth rotating on its own axis. The second is orbital motion, like a planet traveling around its star. Both are simply different forms of angular momentum. The math differs, but the logic holds up. A rotating pattern will just keep going unless something applies a net torque to it. That just means an outside twisting force stepping in to disrupt the flow. Out in space, where friction barely exists and massive objects stay totally isolated for millions of years, this stubborn persistence runs the whole show. Down on Earth, you see this momentum redirected instead of destroyed all the time. A spinning bike wheel fights being tilted. A toy gyroscope feels strangely stubborn right in your hands. An ice skater spins much faster when pulling her arms in and slows down when reaching out. The total momentum stays exactly the same, but the speed shifts purely because the mass changed its physical arrangement. The real secret isn't just that an object happens to be spinning, but exactly how its weight sits around that central axis of rotation. When I look at collapsing nebulae, this is exactly why cosmic spinning becomes totally inevitable. Picture a massive cloud of dust slowly collapsing under its own gravity to birth a new star. That cold cloud doesn't need to be spinning super fast when the process begins. It just needs the tiniest, faintest trace of net angular momentum. That little nudge can come from anywhere. A gentle drag from nearby space, shockwaves from an old supernova, or just tiny random drifts that don't perfectly cancel each other out. The beautiful part is that the spin doesn't need to be huge, because gravity amplifies it. As my telescope watches a cloud shrink, the star stuff gets pulled to the center. With mass moving inward, that locked momentum forces a much faster rotation rate. The physics behind it is surprisingly simple. Widespread mass has huge leverage, exactly like pushing a heavy door right at the handle. But when gravity pulls that mass inward, all that wide leverage is lost. To keep the math balanced, the core must move faster. This speeds up the ice skater, and it's why collapsing star systems spin up entirely. It's not gravity adding spin. Gravity just drags the dust inward, while physics demands the rotational ledger stays perfectly balanced. That wild amplification is one reason Tonight, you and I will explore why the universe always favors a spin. Even when a massive star cloud barely twists at first, gravity crushing it inward eventually whips that tiny motion into a massive, elegant spin. Out there in the dark, a state of perfect stillness is almost impossible to find. The cosmos is loud and restless, packed with constant pulling, endless ripples, and chaotic cosmic currents. So when huge gas clouds fall inward, they never drop straight down to the center. Instead, that hidden rotation grabs hold and spirals everything as it shrinks. But the physics of the night sky are rarely that neat and tidy. Spinning energy is kept perfectly balanced in total isolation, yet nothing in space sits truly alone. Stars are born in crowded neighborhoods. They swap gas and feel the heavy tug of passing giants. Inside a single collapsing nursery, heavy pockets of gas crash together, twisting and dragging on each other. The total spin remains perfectly balanced, but its location shifts dramatically. That beautiful chaos of moving energy is exactly how our cosmic structures get their shapes. Look at how a new solar system is born. The infant star swallows almost all the heavy matter. Yet the wide, sweeping ring of dust holds onto most of the spinning energy. That is by design. It is a direct result of how cosmic momentum naturally travels outward. The gas that drops deepest into the gravity well has to shed its spin to neighbors. Otherwise, it spins too fast to ever reach the star's heart. Violent crashes, magnetic storms in glowing gas, and heavy clumps pulling on each other all work together to push that dizzying energy further out. The slow material sinks to build a brilliant sun. The fast material glides into wide, peaceful orbits. We are left with a dense, burning star and a wide ring. Both sharing the exact same cosmic energy budget, carefully balanced so the star can keep growing without breaking the laws of physics. Young planets inherit their spins from this dusty cradle, shaped later by brutal asteroid strikes and wandering moons. As a new world builds itself, it pulls in rocky debris that is already circling the sun. A massive collision can completely flip its axis or speed its daily rotation. Over millions of years, giant worlds slowly tug on each other, quietly trading their orbital energy. Still, the entire solar system keeps its momentum balanced, except for tiny leaks from stellar winds or dust drifting into the void. That is why planetary spins seem so random, even though every single one of them dances to some rhythm. This hidden twisting force also explains why so many galaxies look perfectly flat. When a giant nebula carries a slight spin, gravity cannot crush it down perfectly from every side. Gas falling from the top and bottom drops straight in, but material rushing in from the sides gets caught up in a runaway orbital spin. Anything carrying enough speed naturally glides into a vast, flat ring where it safely circles instead of plunging. Thick cosmic gases naturally slow down any chaotic up and down movement, grinding that extra motion away through heat and friction. Moving within that flat lane survives indefinitely. The glowing system becomes completely flat. It is simply the elegant math of gravity and friction. Now, let's zoom out together, far beyond our little local solar neighborhood. Entire galaxies spin majestically, holding onto the momentum they gathered when the universe was incredibly young. As an astronomer, I see galaxies twisting because massive neighboring dark matter structures pull on them across the great cosmic web. When ancient dust flows into giant dark halos, it never falls symmetrically. That lopsided cosmic rain creates a gentle twist. As the galaxy shrinks, that momentum carves out the glowing paths of stars. Deep space gas cools and settles beautifully into a delicate, razor-thin spinning disk, while older stars act like ghost particles, drifting freely to build much thicker, warmer halos. When galaxies crash, that beautiful spin scatters into chaotic swarms of stars. But I promise you, the original momentum never vanishes. It simply spreads out among a trillion new orbits, sometimes flinging long tails of shattered gas into deep space. When you and I look through my telescope, the physical proof is waiting. We astronomers measure these cosmic spins easily. Starlight from distant galaxies shifts in color, showing us exactly which side is rushing toward our lenses and which side is slipping away into the dark. For single stars, I track dark spots crossing their surfaces and measure the gentle fading of their fiery light. Through my telescope, I measure a planet's spin by tracking surface storms or listening to radio whispers and magnetic fields. Across all these vast cosmic realms, one simple rule explains why spin survives and why it speeds up as stellar gas collapses inward. If the cosmos preserves this spin, what alters it? The answer is torque. To shift angular momentum, you need a twisting force. Torque needs an uneven push. That is why, out in the deep dark, rotational energy migrates between celestial bodies rather than simply vanishing. Tidal pulls between close-knit worlds trade momentum back and forth between spin and orbit. I watch stars slow down as magnetic fields grip stellar winds, flinging charged particles into the void and carrying their spin away. The gentle gravitational tugs between planets can shift momentum across their orbits. Violent cosmic collisions transfer this turning energy from world to world or scatter it into flying dust. The night sky is full of these cosmic trades, yet they remain trades. The astronomical ledger always balances. This is why you and I will never see a perfectly still universe. In the deep void, there is no drain to catch that spin. A lonely rogue planet drifting through space cannot easily hand its rotation over to nothingness. A star sheds spin through stellar winds, but it will never truly stop turning in our lifetime unless those forces are unusually fierce. A spiraling galaxy alters its spin through massive collisions and galactic mergers. But it never fully rests. The surrounding vacuum is not a frictional sea that drains motion away quickly. Out here in the dark, the turning simply endures, shifts its shape and echoes onward. The reason this turning energy feels so eternal to me is its deep connection to cosmic symmetry. In my field of astrophysics, conservation rules are born from nature's beautiful symmetries. Linear momentum is preserved because the underlying rules of physics remain exactly the same, whether I aim my telescope here or a billion light years away. Energy stays constant because those same cosmic laws do not shift, not from today until the end of time. And the preservation of spin comes from the simple fact that physical rules hold true no matter how I rotate my celestial maps. The cosmos does not care which way I point my lens, up, down, north, or east. The rules remain identical regardless of how you spin. A specific amount of energy is forever locked inside that rotation. That is the profound reason why cosmic spin is so incredibly stubborn. It is not some random guideline. It is woven into the very fabric of reality. I find a quiet elegance in that. The cosmos requires no hidden engine to keep the galaxies turning. Spin naturally emerges because stardust is almost never scattered in perfect, flawless balance. It happens because gravity pulls mass inward, while the universe keeps a very strict tally of momentum. Once that turning begins, it persists, sculpting flat solar disks, stabilizing planetary orbits, and building the eternal architecture of everything from tiny moons to sprawling galaxies. Look closer with me, you can see this spinning momentum as a cosmic memory. Not biological memory, of course, but an immortal, conserved trace of ancient movements and long-gone cosmic imbalances. A planet's day is a turning fossil of ancient dust and early collisions. A star's rotation shows how it was born, shaped by solar winds and magnetic fields. Meanwhile, a galaxy's spiral reveals ancient currents of matter and long-forgotten celestial encounters. The rotation is cosmic history that does not completely fade. When I look up, I find that gentle thought to be strangely, deeply comforting. We live inside a galaxy that keeps careful watch, where even the smallest starry twist is never lost, but gently carried forward and beautifully transformed. In that quiet steadiness, you and I can let our long days loosen their grip. We can feel our tensions unwind, resting safely within the calm reliability of nature's endless rules. Chapter 4, Gravity Turns Falling into Spinning. To most, gravity has a simple reputation: it pulls. It makes things drop inward, crushing stardust into dense, dark places. If you only observe gravity inside a quiet room, that inward reputation seems entirely complete. Drop a stone and it hits the floor, throw it and it arcs down. Down here, everything seems to prefer a straight plunge toward the center. But my telescope reveals the universe is no quiet room, and gravity is far more than a force of inward collapse. Gravity is actually a quiet sculptor of paths. Give a floating asteroid even the slightest sideways nudge, and the massive pull of gravity will never erase it. Gravity gently bends it, a fall becomes a smooth curve. That curve becomes a closed loop, and that loop settles into a stable orbit. This is exactly how gravity turns endless falling into beautiful spinning. It doesn't magically pull rotation out of the void, but reshapes the geometry of travel into an eternal turning dance. Out in space, objects rarely ever fall perfectly straight down. Down is just a local illusion. Tonight, look up at the cosmos with me. Gravity always draws matter together, yet nothing is forced into a single rigid path. When I observe a gas cloud drifting toward a newborn star, it is never like dropping a stone. It is already flowing, pushed by neighboring stars, ancient turbulence, and older gravitational tugs. Because that cosmic drift is almost never perfectly aimed, the material naturally misses the exact center. That simple miss changes everything. It avoids a direct collision. Instead, the object gently sweeps around the star. We call this the birth of an orbit. In basic astrophysics, any small rock approaching a massive planet with just a little sideways drift gets deflected. If it wanders in slowly enough, gravity bends that journey into a quiet, closed loop. If it speeds in faster, gravity simply bends the path as the object flies back out into deep space, but the main takeaway stays the same. Gravity spins a lazy sideways drift into a graceful curve. A near miss becomes a turning path. When we astronomers scale this up to billions of particles, vast structures emerge. Picture a huge dust cloud slowly gathering. This gas never collapses in a perfect sphere. It flows smoothly along cosmic filaments. Material arrives in heavy clumps, streams washing in from every angle. Each brings its own momentum, and these crosscurrents never perfectly cancel out where they converge. That swirling mix creates shear, meaning deep layers of gas smoothly slide past each other. In fluid dynamics, this gentle sliding is how spin begins. It is not a perfect rotation just yet, but you can see a beautiful rhythm where falling and turning become one. As the stardust drifts deeper inward, the powerful focus of gravity makes that spinning sharper. Gravity funnels everything toward the middle, forcing particles into close encounters and gentle collisions. In a nebula, passing closely is more than just crossing paths. It creates intense heat and pressure. Crashing streams spark shockwaves that erase messy, direct collisions, while that smooth sideways drift calmly survives. The cloud radiates away its heat, but it cannot easily shake off that sideways momentum without a twisting force. As that raw energy fades, the dark gas binds tighter together, and its spinning nature takes center stage. I find this detail absolutely crucial. Cooling calms the matter while gravity gently pulls. The leftover sideways drift naturally settles into a peaceful, orbiting flow. You and I see disks everywhere in astronomy for this exact reason. They are elegant, dynamic solutions. It lets matter hug a glowing star tightly without simply plunging straight in. The disk forms a perfect balance between gravity's heavy pull and the sideways glide the matter already carried. Gravity tirelessly drags the dust down, while the orbital speed tries to fling it past. The result is a slow, mesmerizing spin that lasts for eons. Even when we look at rocky debris instead of gas, gravity still turns a straight plunge into a curve. Picture a huge swarm of comets gliding past a growing massive planet. Each rock carries its own speed. Very few are perfectly centered. Most simply sail by with a slight offset. Gravity softly warps those lonely paths into sweeping arcs. Inside crowded planetary systems, endless close encounters shuffle the energy around, locking some asteroids into tight orbits while tossing others out into the dark. Over time, the whole field develops a shared orbital rhythm around the center, because only the orbits that fit the cosmic momentum budget and the local gravitational landscape actually survive. But I also study how gravity creates twisting spin from messy, uneven patches of space. In our perfect mathematical models of round planets, the gravitational pull aims exactly at the dead center. Out in reality, deep space is clumpy and lopsided. When a newborn galaxy is strangely shaped, its own lumpy sections pull at crooked angles. This triggers internal twisting forces, shifting rotational momentum from one spiral arm to another. Even more fascinating for observers, giant neighboring galaxies constantly tug at one another as they expand. The heavy pull from a neighboring cluster never lines up perfectly with the core of the galaxy we are watching. That tiny misalignment pulls like a massive, invisible lever. Across deep time, these tidal twists slowly spin up the entire growing system. Now, gravity never breaks conservation laws to conjure this spin out of thin air. The total angular momentum of any truly isolated void remains strictly conserved. These tidal forces merely trade spinning momentum across different regions, shuffling spin between objects in vast sweeping orbits. When you and I study the cosmic web, we realize absolutely nothing forms in total isolation. Early cosmic structures grow deeply tangled with their many celestial neighbors. Gravity trades spin like a cosmic currency. The beautiful result we observe is that countless bound objects eventually start rotating simply because their birth environment provides gentle sideways tugs and long-lasting twists. While these clouds collapse, gravity quietly filters pure chaos into beautifully ordered motion. Deep inside a falling cloud, paths that cross too closely end in destruction or blending. Meanwhile, material moving too fast simply breaks free. The paths I see surviving are the stable ones. They stay gently tethered and dodge those violent, fatal crashes. And motion tethered to a center naturally becomes a gentle orbit. Over time, the whole system looks much more ordered than its messy beginning. It did not start perfectly neat. Instead, gravity and lost heat slowly molded that wild flight into a calming set of stable, repeating loops. This solves a puzzle we astronomers often ponder. Gravity is strict. It does not bleed off energy as pure heat the way normal friction does on Earth. Even so, these massive gravitational systems eventually relax into quiet balance. This calming effect happens because gravity endlessly trades energy and momentum among countless moving bodies. Some dust grains steal energy and drift outward, others lose it and slowly sink inward. Out in the nebulas, shocks and starlight bleed off even more energy, binding the whole gas cloud tightly together. Yet through all this, that crucial sideways drift never vanishes. It becomes the deep foundation of the beautiful, spinning structure taking shape in the dark. You and I can see this magic whenever we watch stars being born. A young star ignites inside a churning nursery of gas, usually stirred up by the ghosts of ancient, dying suns. Gravity draws a patch of that dark cloud together, but the pull is rarely a straight line. As material rains down, it flattens into a single plane, forging a beautiful accretion disk. Through my lenses, that glowing disk is where pure falling transforms into endless spinning. Gas in the disk desperately tries to sink toward the center, but it first has to shed its twisting momentum. So it creeps inward slowly, handing its spin outward through deep friction. The rotation I observe is definitely not just for show. It is the main engine letting gravity feed the young star while obeying the strict laws of motion. We see this exact same rhythm around dense cosmic shadows like neutron stars and black holes. When stellar gas plunges toward a massive gravity well, it rarely drops straight down. It sweeps in sideways, spiraling gracefully through a glowing disk. During that long spiral, the gas burns violently hot as the sheer pull of gravity turns into extreme, flowing heat. That swirling ring shines fiercely, creating some of the absolute brightest beacons in our universe. Here again, the spinning is mandatory. It is simply what falling looks like when missing the exact center is the cosmic rule, not an accident. Long after planets settle down, gravity still twists falls into smooth spins using close encounters and tidal tugs. When an asteroid sweeps near a planet, it practically never flies on a dead straight path toward the core. It drifts in at an angle and gravity bends the journey. If that flyby bleeds enough energy, maybe dragging through an atmosphere or ancient dust ring, the wanderer becomes a captured moon. Let's follow this closely. If it dodges capture, it swings right past, trading momentum with the planet while our sun or nearby moons pull the strings. These quiet dances slowly tweak orbits and softly rewrite how spin is shared across the whole solar system, keeping the total balance perfect while changing individual paths. Looking at massive galaxies, the same beautiful story repeats on a truly grand scale. Cold matter flows down vast web filaments into heavy pools of dark matter. These rivers never align perfectly, so every plunge carries a sideways drift. Nearby cosmic halos exert strong tidal pulls, twisting those incoming rivers. Across billions of years, the finished galaxy inherits a master spin and a beautifully distinct orbital layout for all its stars. If that star city is rich in gas and left alone, everything settles into a majestic rotating disk. But if galaxies collide, that smooth rotation shatters into a chaotic swarm of starry motions. Yet even then, the ruined, merged system still guards its total spin. It just hides that spin inside the wild loops of billions of stars, rather than one flat plane. So what do you and I see? Gravity never just pulls straight down. It bends flight into sweeping arcs, preferring orbits whenever any sideways drift exists. It molds rivers of dust into spinning carousels when lost heat leaves the core laws of momentum perfectly intact. It allows deep cosmic twists, trading spin among celestial neighbors out in the quiet dark. When I map the skies, perfect alignment is rare. Gravity makes turning a natural outcome of falling. This cosmic reality creates a profound emotional contrast, one that is deeply soothing when we let it settle. I have learned the universe isn't just a chaotic place where everything inevitably crashes together. Gravity could have built a cosmos of endless impacts and quick deaths. Instead, it allows for beautiful, stable motion. To me, orbits look like a peace treaty between motion and attraction, staying close without ever being consumed. I find a quiet comfort in that. Most things out there don't survive by fighting gravity. They survive by moving right along with it in perfect balance. Tonight, you and I are part of that exact same universe, drifting along curved paths and steady turns. It is enough to let the sharp edges of your day soften, knowing that even a long fall can become a very gentle orbit. Chapter 5, From Clouds to Disks, Why Worlds Form in Spinning Rings. As an astronomer, I know a planet begins long before it has a surface, air, or a name. It starts as a tiny shift in a cold, empty cloud, a slight tendency for the cosmic dust to spin as gravity pulls it in. Through my lens, that rotation doesn't look like a disk at first. It looks like pure chaos, just violent turbulence, drifting gas, and space dust with no clear plan. Yet night after night, I watch nature guide that drifting matter into our most recognizable astronomical shape, a flattened, spinning disk. New worlds form inside these rings, not by random chance, but because gravity and momentum create disks when star stuff cools, crashes, and finally settles. the massive clouds that give birth to brilliant stars. And planets are called molecular clouds. They are giant pockets of interstellar gas, freezing cold so molecules survive. We observe they are never still. They churn with turbulence, whipped up by stellar winds, exploding supernovas, and the slow, grinding rotation of the galaxy itself. Invisible magnetic fields also weave their way through these dark clouds. To us humans, these fields feel weak, but they matter immensely because the stellar gas carries an electrical charge. Charged particles react to magnetic forces, and since they smash into neutral atoms, these magnetic ripples end up steering the entire flow of the cloud. The birth of a star begins when a cloud pocket grows gravitationally unstable. Cooling is crucial here. Gravity packs material tight, spiking pressure and heat. The cloud has to vent that heat into space to keep collapsing inward. Deep inside cold molecular clouds, energy bleeds off through glowing molecules and tiny dust grains that soak up the heat and beam it away. When cooling works, gravity beats out internal pressure. A dense core forms and shrinks. Even now, this infant core dwarfs our entire solar system. Through our older telescopes, it might look round, but honestly, it is never perfectly spherical or evenly mixed. We see thick clumps, glowing threads, and shifting speeds. Even if its overall spin seems tiny, it is almost never zero. In the raw chaos of deep space, opposing currents never cancel out perfectly. As gravity crushes the core, that tiny leftover spin starts to dictate everything. As the core shrinks down, that saved momentum forces it to spin faster and faster. Suddenly, the whole collapse shifts its behavior. The heart of the cloud tries to pack tighter, but the rapid spinning pushes back sideways. Matter falls straight down along the poles, but around the equator, you and I can see that inward plunge twist into a wide, sweeping spiral. This marks the physical birth of the disk. The system naturally flattens out, cutting straight across the spin. Gas rushing in from top and bottom smashes together, venting energy and settling into a smooth middle layer. Any stray movements across this flat plane get quickly erased by violent, heated collisions. But movements inside the flat plane survive as an endless orbit. Over thousands of years, the dying cloud feeds fresh gas into this flat, spinning ring circling the dense core. What starts as a thick, messy, swirling storm gets carved by gravity and heat loss into a beautifully perfect disk. That glowing center slowly becomes a protostar, not a real, stable sun like ours just yet. It is just a hot, heavy mass powered by gravity crushing it inward. Around it, the massive disk holds the dust. You and I aren't guessing. I routinely photograph actual disks circling young, newborn stars. With today's observatory arrays, I can even spot stunning rings and deep gaps carved directly into those disks. It tells me that unseen worlds are already shaping the dust, while their infant sun is barely born. These planetary disks are not theoretical decorations. When you and I look deep into the galaxy, we see these disks everywhere. They are the natural result of collapsing clouds spinning up. In my telescope, this disk is never a static plate. It is a living river of gas, constantly swirling around the young star. But those orbits are rarely perfectly stable for every parcel. We observe intense friction inside the disk. Turbulence and magnetic forces act like heavy stresses, pushing the rotational energy outward. This shifting energy lets gas slowly drift inward to feed the growing protostar. Without it, the material would just stay stuck in endless orbit. So as astronomers, we know the disk's spin does more than build planets. It completely controls how the star grows. At the exact same time, it acts as the birthplace for solid matter. The dust starts as microscopic grains drifting through the interstellar void, usually wearing heavy coats of ice in the dark outer edges. Inside the disk, they constantly crash together. Sometimes these grains shatter, but often, if the crash is gentle or the ice is thick enough, I imagine them just sticking together. Through millions of tiny impacts, those grains slowly grow into little pebbles, then larger clumps. We study how the thick gas of the disk drags heavily on these growing solids. That drag makes rocks drift inward. It also forces particles of certain sizes to pile up in distinct rings, right where the gas pressure suddenly shifts and slows down. This dance between gas and dust is exactly why protoplanetary disks are such incredibly fertile nurseries for new worlds. The disk creates a crowded, thick environment. Collisions happen constantly here. The flat geometry traps all the floating material in one tight plane, making it much easier for wandering solids to meet. If this were a massive spherical cloud, particles would just miss each other in the dark. But in a disk, every path is locked, orbits packed tightly into a thin sheet, making actual growth inevitable. As those solids finally gain mass, gravity wakes up. The tiny dust grains only cared about air resistance and random bumps. Now the larger rocks begin pulling each other close. Once these objects get massive enough, we see runaway growth. The biggest bodies grow the fastest, using their strong gravity to sweep up everything in their path. This sudden rush creates the very first planetesimals and protoplanets. Their heavy movements churn the gas, whipping up wild speeds that cause massive collisions. Some build worlds, others destroy them. The final planetary system depends on chaotic forces. Things growing, shattering, drifting inward in the fading gas. If you and I map the heat, we would notice the disk is never uniform. Close to the young star, it boils. Drift further out and it freezes. This temperature drop dictates exactly what materials can harden into solids. In the hot inner zones, I only find stubborn materials like heavy metals and tough silicates. Out in the deep freeze, fragile gases harden into ice, adding huge amounts of solid building material. This split in the cosmic inventory explains why I usually spot small rocky planets huddled close to their home star. And it shows why giant gas worlds, needing massive icy cores to capture thick atmospheres, thrive out in the freezing dark. This disk, as we astronomers see it, is no empty stage. It is a rich, temperature-controlled nursery that carefully decides exactly what kind of planet will be born and where. That ancient spin also locks in the permanent direction every new planet will eventually orbit. Since the entire disk flows one way, almost every world we find orbiting that star ends up marching in that exact same direction. Even their daily rotation shows that shared birth, though violent asteroid impacts and slow tidal forces will eventually tilt their axes. So the star's disk permanently stamps a quiet family resemblance onto the whole system. A shared flat plane, identical orbital paths, and a perfect spread of elements carved by ancient heat. Still, my observations show these disks are rarely perfectly calm or perfectly aligned. They heavily warp if neighboring stars pull on them, or if fresh gas falls in from weird, conflicting angles over thousands of years. Wild turbulence spins up deep eddies and strange pressure pockets. Invisible magnetic fields trigger massive instabilities, violently stirring the gas. These invisible storms matter to us. They sweep up dust, carve dark gaps, and completely alter how baby planets migrate. It is an incredibly restless place where tiny shifts trigger massive planetary changes. That is why every solar system we discover looks so wonderfully unique. The exact same laws of physics build a familiar skeleton. While time and space create endless diversity, you and I might wonder how these disks actually die, because they never last forever. Fierce young stars blast hot radiation and heavy winds, slowly boiling the gas away. Sometimes, brutal ultraviolet light from giant neighboring stars just melts the disk entirely. I watch young stars devour their disk material. I see planets clearing gaps and carving pathways, speeding up the disk's evolution. Over time, you and I see the gas fade, leaving just a debris ring of dust and leftover rocks until even that quietly thins out. As astronomers, we know the window for building gas giants is brief. Timing dictates everything, deciding if a solar system gives birth to massive planets or just quiet, rocky little worlds like ours. In my line of work, that classic spinning pancake image is actually no mere metaphor. It beautifully captures the core physical reality. When I model a collapsing cloud with slight angular momentum, I watch collisions and energy loss gently guide the stellar dust into a flat, rotating structure. Inside that cosmic cradle, solid materials can grow quite efficiently, where orbits become beautifully organized, letting planets form and safely circle their star without immediately collapsing inward. For us observing the cosmos, the disk is just nature's way of turning loose clouds into stable architecture. Let's fold this into our larger story without simply repeating what we already know. We already saw why motion persists and how gravity amplifies tiny cosmic asymmetries. But tonight, my focus is far more intimate. I want to trace the exact path from dark molecular cloud to a young star, showing why that disk is the absolute perfect planetary cradle. The rotating disk is never just some extra feature added later on. I see it as the vital mechanism managing angular momentum, quietly allowing matter to concentrate into a bright star and a brand new family of worlds. As a scientist, I find something quietly astonishing about that. The Earth we stand on, with its deep oceans and living cells, traces directly back to one of those thin, spinning sheets of dust around a newborn star. The cosmos never built our planets by simply placing them carefully into the void. Instead, I watch it let clouds collapse and disks emerge, allowing countless tiny collisions to slowly assemble majestic structures from drifting dust. When I end a long night of telescope observations, it calms me to remember we come from cosmic processes that are incredibly patient and deeply lawful. And that even out in this vast dark universe, beautiful order arises gently from motion. Chapter 6, stick with me as we pivot to why planets spin and why some don't. At first glance, a world's rotation looks like a wonderfully simple trait. A world turns, day gently follows night, and that rhythm just feels completely natural and inevitable. But when my colleagues and I compare different planets in our solar system, that simplicity shatters. Some worlds spin furiously, others crawl. Some tilt gently, while others lie completely sideways. Some rotate with their orbital flow, while a rare few boldly spin completely backward against the grain. And some celestial bodies, especially many of the moons I track, barely seem to spin at all. They are tidally locked, forever showing the exact same frozen face to their parent world. To astronomers, these quirks aren't random. They're the violent fingerprints of formation, ancient impacts, core physics, and long gravitational negotiations stretched across deep time. The basic cosmic starting point is inheritance. Planets are born inside that rotating disk around a young star. So, all that raw celestial material already shares a dominant direction of sweeping orbital motion. As we watch dust grow into pebbles and eventually massive bodies, every single collision and gentle merger carries its own angular momentum. Even if these early protoplanets crash at wild angles and chaotic speeds, the overall spin of the disk heavily biases the final average outcome. A growing planet naturally receives far more pushes in the disk's dominant direction than against it. That fundamental rule explains why, generally speaking, I see most planets ending up rotating in the exact same direction they orbit around their host star. But the moment we look past those broad, general rules, the data gets wonderfully complicated. That is because any individual planet's spin remains exquisitely sensitive to pure cosmic chance. In physics, spin builds from vector addition, so direction truly matters. One massive, catastrophic impact can dump more angular momentum than a million tiny pebble strikes. It can hit at angles that aggressively tilt the planet's axis or even completely reverse its rotation. Early solar systems are crowded, highly energetic places. Bodies violently collide, merge, scatter, and sometimes completely eject one another. In that chaos, I read a planet's final spin as a historical summary. It is the cumulative record of countless small collisions, punctuated by a few massive, decisive events dominating the final outcome. This becomes remarkably clear when I study a planet's axial tilt. If a world grew strictly through perfectly aligned accretion inside a stable disk, we would expect straight, perpendicular axes. But as my telescope reveals every night, real solar systems are never that tidy. Collisions arrive with wild offsets. Protoplanets get perturbed by heavy neighbors. The dust disk itself can be violently stirred. The resulting chaos means planets usually end up tilted. So what do you and I make of this? Modest tilts imply normal, messy accretion. But extreme tilts strongly suggest massive late impacts or gravitational tugs played the leading role. Let's look at our own Earth. Its current spin feels so calm and steady, but its past was born from absolute chaos. In my field, the leading theory for the moon's birth is a massive collision during our young world's early days. A violent strike that completely shattered Earth's original rotation and tilt. We still debate the exact physics today, but the core truth remains solid. Cosmic collisions rewrite how a world turns. They stretch out days, knock axes sideways, and blast debris into orbit that eventually clumps into quiet silver moons. A planet's rhythm is never just inherited from birth, it gets edited. So why do some planets we observe barely seem to turn at all? That sluggish motion usually comes from tidal braking, and out here, tides mean much more than oceans. Any large mass feels an uneven pull from gravity. The side facing its star gets tugged just a bit harder. This uneven grip actually stretches the rock, creating massive tidal bulges. If everything lines up perfectly between the two masses, there is no twisting force at all. But real planets resist stretching. Deep internal rock friction, along with swirling oceans or thick atmospheres, causes those heavy tidal bulges to drag slightly behind or push ahead. Gravity catches on that crooked bulge, stealing energy from the spin and pushing it into orbit. Over millions of years, this invisible drag slows the planet down and reshapes its partner's path. It is the reason we see moons become tidally locked, forever showing just one quiet face to their host planet. People often ask me if the moon has simply stopped spinning entirely, but that is not true. It still turns, it just perfectly matches the slow rhythm of its orbit. We see this pairing all across the cosmos because it is a deeply peaceful, stable end state for celestial bodies. Once they find that perfect synchrony, the twisting forces fade away, locking them together for billions of years. These tidal forces also shape planets, especially those huddled dangerously close to their stars. When I observe distant exoplanet systems, I see worlds trapped in the fierce tidal grip of their suns. We expect these fiery worlds to become locked, roasting one side endlessly, though thick winds, weird orbital shapes, and deep rock layers can twist the final outcome. Right here in our solar system, Mercury provides a rather subtle, fascinating variation. It is not simply locked face to face. Instead, my colleagues and I see it trapped in a strange resonance, balancing intense solar tides against its slightly stretched orbit. It reminds us that cosmic tides do not always force the exact same outcome. They simply find the calmest resting state allowed by the system's unique, chaotic history. You and I might wonder then, why do certain planets spin entirely backward against the flow of space? That backward roll is a clear sign to astronomers that a world's spin was violently interrupted. Venus is our classic example. It barely turns, lazily rolling opposite to almost everything else out there. Our current models suggest this strange behavior comes from a long, messy evolution, not just one lucky strike. It could be the deep, steady friction of the sun dragging against that incredibly thick, toxic atmosphere. Or internal heating mixed with a few colossal impacts early on that shattered its original momentum. But the overarching physics remains beautifully clear. A world's rotation can be entirely rewritten by its past, and spinning backward does not require some exotic, unknown magic. It just needs time, force, and brutal history. Uranus offers a completely different surprise. Through my telescope, its axis is tilted so extremely that it practically rolls along its orbital path. It sometimes aims its poles straight at the sun. Gentle dust gathering cannot explain that wild angle. We believe it took a massive, catastrophic blow to physically tip the ice giant over during the dark, chaotic dawn of our young solar system. Whatever the exact violent history, the truth is clear: planets can be knocked sideways, leaving their tilt as a permanent scar of ancient trauma. Mars shows us something else: the sheer instability of a planet's tilt over eons. A world's axis can drift, tracing a slow circle in the dark like a wobbling top, tugged constantly by the gravity of passing planets. Thankfully, our oversized moon acts as a steady anchor for Earth's own tilt. It prevents the wild, chaotic swings that would otherwise happen. Mars lacks a large moon, suffering wild climate swings as its axis shifts. As you and I can see, a planet's spin is never just a simple number. As an astronomer, I see rotation as a living, shifting, gravitational dance. A world's hidden anatomy matters deeply. Through our instruments, we see planets aren't just solid rocks. They hide liquid cores, heavy mantles, rolling oceans, and thick atmospheres. Deep inside, these layers secretly trade momentum back and forth. Right here on Earth, our winds and restless seas exchange momentum with the rocky crust, stretching out the length of our days ever so slightly. Over deep time, the friction of our oceans has gently slowed the planet down. So even without massive asteroid strikes, a planet's spin slowly drifts. The internal friction and the shifting weight of its layers do the quiet work. How weight is distributed inside a globe dictates how it reacts to outside gravitational pulls. When a fast-spinning world bulges outward at its equator, it casts a very different gravitational shadow than a perfectly round, quiet sphere. That slight bulge catches the tug of its host star, altering the world's slow wobble, shaping its orbital fate in our cosmic charts. Across millions of years, deep within the planet's core, the slow cooling and settling of iron can shift how tidal energy burns away, subtly changing the exact speed of its daily rotation. To astronomers, planetary spin is wonderfully varied, yet deeply logical. The basic laws of physics never waver. Momentum is always preserved, twisting forces shifted around, while energy loss dictates how smoothly the system settles into a stable, quiet state. The beautiful variety comes from unique cosmic histories. A young world that avoided major strikes spins calmly, matching its birthplace. But a planet shattered by a late collision might roll on its side or spin backward completely. A world hugging its star might become tidally locked, doomed to face one way forever. Gas giants feel thick atmospheric tides that gently push their rotation over the eons. In my research, these aren't isolated little events. They are just different paths through the very same physics. Look through the lens with me for a moment. A planet's spin shows us not just its present motion, but everything it has endured. To us, tilts and spin rates are like deep rock layers, completely written in celestial motion. They lock away the echoes of ancient violence, long after lava flows cool and atmospheres drift away. A living planet might melt its craters, bury its history in sand, and renew its crust, but its rotation still whispers the secrets of ancient impacts and tidal pulls. I find a profound, quiet peace in that thought. A world's day isn't just a ticking clock. It's an epic tale, the span of a sunrise, the slant of winter, the steady climate, and even the hope for life, all depend on the slow, faithful evolution of a planet's turning. The cosmos never hands us carbon copies of rocky worlds. It lets them form, crash together, settle down, and slowly bargain with gravity until each finds a unique rhythm. Standing under the stars, that makes human rhythms feel a little less fragile. You and I live on a globe shaped by blind chance and deep laws, yet its gentle turn remains perfectly steady, granting us a safe place to build a life. When your earthly worries feel heavy, look up. Remember you are cradled by a quiet motion far older than memory. A silent planetary sweep that spins on, completely unbothered by human thought, gently carrying you forward into rest. Chapter 7, Tides, the slow brake pedal of the cosmos. If gravity brings order to the void, then tidal forces are exactly why that cosmic motion slowly changes its pace. Through our lenses, tides aren't flashy like a meteor strike. They don't flash across the sky as one single, terrifying event. Instead, tidal forces are incredibly patient. They chip away orbit after orbit, year after year. They silently convert raw mechanical energy into pure heat, softly shifting momentum from one spinning body right onto another nearby world. In my view, tides act as the galaxy's gentle brake pedal. They mold orbits and spins over time, requiring absolutely no explosions, impacts, or sudden planetary doom. The math starts with a simple truth. Gravity pulls unevenly across any large shape. A planet isn't just a tiny, mathematical dot. Moons and stars are massive bodies. Every single one of them has a near side and a far side when they orbit near a companion in space. The side facing the companion feels a slightly heavier gravitational drag. It seems like a small difference, but over eons, it physically stretches the entire world. This creates a tidal bulge, a very soft stretching along the invisible line connecting the two spheres. Here on Earth, let's picture the ocean's tides. The water reacts to these competing pulls in the Earth's daily spin, forming two massive swells of water on opposite sides of our blue globe. But water is only what we easily see. The solid bedrock actually breathes too, rising and sinking in tiny, measurable amounts. Even our sky experiences tides, fueled by the warmth of the sun and the invisible tug of gravity. So tides aren't just for sailors. To an astronomer, they are a vast gravitational truth, acting on any large object floating closely past another heavy mass in the dark. Look up with me. A flawless, frictionless planet would bulge perfectly along the line of gravity's pull. That tidal bulge stays perfectly aligned. Gravity finds absolutely zero grip to alter the world's gentle spin. But through my telescope, real planets aren't perfectly elastic, and real oceans aren't frictionless. Deep inside, solid rock holds friction. Thick liquid layers churn, and complex ocean currents grind heavily against rugged coastlines and dark, silent seabeds. Because of this messy friction, the tidal bulge shifts slightly out of alignment. When a planet spins faster than its companion moon orbits, we see that massive bulge dragged just ahead of the line connecting their centers. If the world spins slower, the bulge falls behind. To us astronomers, that tiny angular offset is everything. The moment that bulge drifts off center, gravity yanks it. The orbiting moon's gravity fights to pull that bulge back into perfect alignment. In doing so, it creates a twisting torque that alters the planet's rotation. Simultaneously, this twisting force acts upon the orbit itself, proving that every cosmic action demands a reaction. Invisible angular momentum flows gracefully between spin and orbital motion. Energy bleeds away as warmth. The celestial system evolves. Right beneath our observatory floors, Earth does this now. Earth completes a spin each day, while our moon drifts slowly. Because we rotate faster than it orbits, our ocean's tidal bulge rides just ahead of the invisible line connecting us. The moon's gravity drags backward on those ocean swells, applying a gentle cosmic brake to Earth's spin. Over epochs, our earthly day lengthens by a fragile fraction. Our ocean bulge also tugs forward on the moon, gifting it orbital energy. Slowly, steadily, our pale companion spirals further out into the dark. You and I don't have to guess. We bounce lasers off lunar mirrors to measure this exact long-term tidal transfer of energy. Earth slows down and the moon drifts away, but notice the beauty of orbital mechanics here. The angular momentum isn't destroyed. The universe just shifts it around. The total angular momentum of our Earth and moon remains beautifully conserved. Disregarding tiny leaks of radiation and a few subtle gravitational whispers. Tides simply steal spin from the host planet, hand it to the orbiting moon, and melt a little mechanical energy down into pure heat. Out here in the dark, that warmth is never wasted. It breathes thermal life straight into the very cores of these celestial bodies. When I observe distant moons, this tidal friction burns so hot it becomes their primary power source. Suddenly, cosmic tides are much more than a brake pedal. They ignite into a geological engine, sustaining violent internal activity across the icy void. The most brilliant example I capture on camera is Jupiter's violently volcanic moon, known as Io. Io traces a stretched orbit, constantly tugged and warped by the gravity of neighboring moons. This celestial dance keeps the path elliptical. As Io sweeps around Jupiter, shifting tidal forces stretch and crush the moon without mercy. It flexes constantly. All that deep rocky friction sparks immense heat, fueling massive, endless volcanic eruptions. Up there, gravity isn't just slowing a rotation. It is physically powering a shattered, molten surface. As astronomers, we track similar tidal heating inside moons like Europa and Enceladus, hinting at vast, hidden alien oceans. Deep within those icy spheres, rhythmic tides keep buried oceans liquid. The cosmic implications for life are staggering. This profound heating proves we must use the word brake carefully. These dissipative processes literally melt organized orbital mechanics into raw thermal warmth. It acts as a brake on momentum, sure, yet that resulting warmth sustains deep complexity, keeping frozen worlds beautifully alive. It builds a lasting, beating heart of internal energy far out, where sunlight grows hopelessly dim. Cosmic tides whisper softly, yet completely transform planetary systems. They are exactly why my telescope reveals so many tidally locked moons. Any small, close satellite endures a brutal gravitational grip from its massive host planet. Millennia pass, and that grinding internal friction forces the moon to synchronize its spin perfectly with its orbital journey. Once synchronized, the rocky bulge stops rolling across the lunar crust. It locks into place. The twisting torque instantly fades away. The moon freezes in a stare, forever showing just one face to its host. In astronomy, this isn't rare. It is the ultimate destiny for most tight lunar systems, simply because a locked orbit is incredibly peaceful and stable. Even massive exoplanets fall into tidal locks, especially those huddled dangerously close to their searing suns. When scanning the galaxy, we mostly catch these tight orbit worlds, mainly because they cross our instruments so frequently. The star's gravitational drag is so immense, these planets halt their spin in a cosmic blink, long before their stellar system grows old. A locked world endures permanent, blistering daylight on one half, while the dark side freezes in eternal, starless night. You and I can imagine how fiercely that shapes an alien climate. As an astronomer, I look for those hidden details, a world's atmosphere, its deep interior, and whether its orbital path traces a perfect circle. Even in this tidal story, every nuance matters. Another major outcome we see is orbits smoothing into circles. Through our telescopes, we watch tidal forces calm an eccentric orbit. The shifting gravitational stress generates friction, slowly damping the motion. The star system bleeds off mechanical energy, though angular momentum stays locked. Gradually, the chaotic path rounds into a calm circle. This explains why many close moons and planets we chart have nearly circular orbits. We do find strange exceptions. Moons like Jupiter's Io stay eccentric because ongoing gravitational tugs constantly disrupt their paths. These gravitational dances keep those eccentric paths alive, fueling intense tidal heat for eons. Tides also shape axial tilt and planetary precession. A spinning world is never a perfect sphere. That rapid rotation creates a slight equatorial bulge. Stars and moons tug on that bulge with gravitational torque. This forces the planet's axis to slowly wobble, tracing a giant cosmic circle. Right here on Earth, this subtle precession is exactly why the timing of our equinoxes slowly drifts over the ages. Tidal friction also shifts a world's obliquity, gently rocking the planet until its tilt locks into a stable, lasting rhythm. These changes take eons, but over deep time, they completely define a world's climate and stability. You and I have already explored how celestial rotation is born and why the universe guards angular momentum so fiercely. Let's build on that foundation. Tides are one of the clearest ways the cosmos moves, that spinning energy around long after a system forms. They act as an engine of cosmic evolution, slowly turning a wild, chaotic mess of spinning rocks into a quiet, deeply synchronized celestial dance. Given enough time, tides synchronize and reshape entire worlds. Yet they do not always make things simpler. Sometimes gravitational tugs spark incredible complexity. If a planet has vast oceans, the very shape of its continents can amplify tidal friction, draining away immense energy. If a world hides deep, complex layers, the shifting speeds between its core and mantle change everything. When several moons cross paths, their gravitational resonance keeps eccentric orbits alive and planetary cores burning. This tidal story is never just a boring fade to black. It is a slow cosmic negotiation, where the final shape depends entirely on local environment. Even here at home, tides do more than shape our coastlines. Over deep geological time, this tidal friction has steadily slowed our rotation, stretching out the day. When my colleagues study ancient fossils and deep sedimentary rock, they find proof. Millions of years ago, Earth spun much faster, and our days were significantly shorter. As our moon slowly drifts further away, that growing distance has profoundly influenced the long-term stability of Earth's tilt. Many of my fellow astronomers suspect tides churned our early oceans, regulating the ancient climate and creating the perfect cradle for life. We still debate those mysteries in the observatory, but the fundamental tidal physics remains rock solid. Gravity bleeds away energy and trades momentum between spin and orbit. Out in the deep universe, these same forces decide the ultimate fate of close binary stars. When two massive suns orbit tightly, they actually raise giant tides on one another. Eons pass and those invisible pulls lock their stellar rotations into perfect harmony, rounding out their paths. In extreme cases, tides drag those stars down into fatal orbital decay. If friction bleeds orbital energy fast enough around dense, compact stars, we witness tidal disruption, A wandering planet ventures too close, and the brutal gravity simply shreds it apart, overpowering its own structural strength. It is a dark, violent side of tidal mechanics, yet it relies on the exact same differential gravity we see out our windows. So tides truly rule the cosmos. Uneven gravity physically stretches worlds. Friction causes lag, lag creates torque. Torque transfers momentum, and friction turns raw mechanical motion into deep planetary heat. Over millions of years, this engine stretches out days, rounds off orbits, ignites deep volcanism, warms hidden subsurface oceans, and tidally locks sister worlds forever. Through my telescope, it is the most elegant way the cosmos edits rotation, requiring absolutely no violent collisions. There is something deeply, quietly moving about that. The cosmos is filled with blinding supernovae, but these slow, invisible forces often do the most profound reshaping. Gravity's tide is always there, always working in the dark, invisible unless we study the data or wait a billion years. It reminds astronomers like me that change does not have to scream to be real. As you and I gaze up tonight, take that as a gentle reflection. Your own life does not have to be totally transformed in one dramatic instant. It can soften and change through tiny, steady adjustments, just like a quiet tide returning again and again. Remember, you are part of a universe where even the most violent, immense motions are gradually guided into perfect calm. Let that cosmic patience wash over you and carry you toward rest. Chapter 8, From Birth Speed to Magnetic Braking, Stars Spin 2. As an astronomer, I often hear people talk about stars like simple, steady lamps. Through my telescope, I see dynamic fluid spheres. Rotation is truly their most fundamental cosmic identity. I've watched nebulae collapse to birth these stars, and they never arrive without a gentle twist. As that protostar shrinks, the twist amplifies. These youthful suns spin far faster than the mature, middle-aged stars we usually observe in the calm night sky. Yet they cannot keep up this youthful speed forever. Over cosmic time, mysterious new processes take hold, and we notice the star's rotation begin to slow. The most vital force at play here is magnetic braking. A slow, quiet drain of momentum, carried off by magnetized stellar winds. Tonight, you and I will explore how stars spin, and how they gracefully change that rhythm through physics written deep into their glowing plasma and magnetic fields. A star's early rotation is a pure tale of inheritance and collapse. When a heavy pocket of a molecular cloud bows to gravity, it drags its original momentum inward. As this cosmic dust falls inward, that very same momentum squeezes into smaller and smaller radii. Naturally, the rotation rate surges. This newborn protostar can spin incredibly fast. During these early phases, we see mass flowing in through a surrounding disk, which is also rotating. This accretion feeds the star both mass and swirling momentum. If a young star simply swallowed everything without limit, it would spin so violently that extreme centrifugal forces might tear its glowing equator apart, fighting gravity itself. But I've learned nature rarely allows that chaos. Momentum is carefully regulated out there. One reason is that young stars are never truly isolated, lonely spheres of gas. They stay intimately anchored to their disks and stellar environments. When I map the space near a young star, I find dense magnetic fields. These fields tether the sun to its inner disk, allowing powerful torques to exchange energy. Simply put for us, those magnetic lines act like a set of unseen ropes, tied deep within the spinning star and dragging against the disk. This cosmic bond will either speed the star up or slow it down, dictated entirely by the shifting rotation rates of the disk at different distances. My colleagues and I still study the math, but the outcome remains clear. Star and disk interactions suit that rotation during early life. This prevents young stellar objects from reaching the chaotic, extreme spin rates that pure collapse would otherwise trigger. Let's look closer. A star's rotation is almost never rigid. Because they are fluid, different depths and latitudes spin at completely different speeds. Our own sun shows us this beautifully. Its equator spins far faster than the poles. We call this differential rotation, and it is no minor astronomical detail. This uneven spinning is the essential spark needed to generate massive magnetic fields through dynamo action. Inside our sun, hot plasma bubbles up while cool plasma sinks, driving convection. This boiling motion, paired with rotation, weaves currents together. Those rivers of plasma build and sustain enormous magnetic fields that never rest. They constantly twist, break, and reconnect. Through my lenses, this looks like violent sunspots, solar flares, and shifting magnetic patterns across the decades. Across the cosmos, especially in cool dwarf stars with boiling outer layers, the magnetic dynamo and rotation are permanently bound. A faster spin creates intense magnetic activity. That strong magnetic pull then increases how much rotational energy is lost to solar winds. It forms a beautiful feedback loop, forcing stars to gradually slow down as they age. Here is how it works. The star exhales a gentle wind of particles, mostly protons and electrons, drifting outward into the void. Without a magnetic field, this breeze would blow away some mass, but it would barely touch the star's spinning momentum. With a magnetic field, the story changes entirely. Because this wind is electrically charged, those tiny particles are steered by magnetic forces. The magnetic web forces this escaping plasma to rotate alongside the star, reaching out into space far past the glowing surface. Acting like a giant invisible lever arm, this widened wind drains away far more angular momentum than it ever could alone. The star feels a heavy, dragging torque as a result. We call this magnetic braking. The star's rotation finally slows down because that magnetized solar wind behaves like a long handle, quietly pulling momentum away. The star isn't breaking the laws of physics or destroying this precious momentum. It is simply handing its spin over to the departing plasma, letting it drift silently away into cold interstellar space. The total momentum of the cosmic neighborhood remains perfectly balanced, even as the old star spins down. You and I observe this directly. To start our journey tonight, look at a star cluster with me. When stars form together, we measure how fast they spin by tracking dark spots rotating across their faces. What I always find beautiful is that young stars spin wildly. They have this huge range of rapid speeds, while older stars of the same mass tend to calm down. They spin much slower and their speeds balance out. Seeing this steady slowdown over time is exactly what convinced my colleagues and me that magnetic braking is real. It actually lets us use a technique we call gyrochronology. If we are careful, a star's spin rate acts like a cosmic clock, revealing its true age. But the braking process is not exactly the same everywhere. A star's mass changes its deep internal structure. Really massive giants have unique outer layers. The crushing pressure of light drives fierce stellar winds, overpowering the churning gases we see in smaller bodies. As an astronomer, I watch these giants blow away massive amounts of material and spin energy, but their magnetic fields behave very differently from our own sun. On the other hand, tiny stars boil from within. This churning changes their magnetic engines completely. We are still mapping exactly how they evolve. Ultimately, the dance of magnetism and time depends on what a star is made of, and as a star ages, its spinning rhythm shifts. During the long, quiet middle years of a sun-like star, its size barely shifts. Magnetic braking quietly takes over, pulling on the star and slowing it down over eons. Years later, that aging star swells into a red giant. Its outer layers balloon outward, completely scrambling how its spinning energy is shared. If nothing moved around inside the star, that massive swelling would force the surface to slow to a near crawl. In reality, through my lens, I see internal waves shifting that energy around. The blazing core and outer shell actually spin at totally separate speeds. By watching these distant stars vibrate, a science we call asteroseismology, we see many aging stars have cores spinning far faster than their outer layers. This is where you and I realize the inside of a star is a beautifully complex mystery, far from a simple, settled equation. When I observe newborn stars, their rotation and fiery activity wildly fluctuate. Their young magnetic fields are incredibly tangled. Plus, the way they pull in surrounding cosmic dust happens in sudden, unpredictable bursts. I watch glowing streams of gas follow magnetic lines to the star, crashing onto the surface and forging blazing hot spots. These blazing patches create light shifts that help me track the rotation. Meanwhile, intense magnetic winds blast outward, draining spinning energy away from both the infant star and its surrounding disk of dust. During those early moments, I often see brilliant jets of gas shooting straight out from these newborn stars. We believe these deep space fountains act like a release valve. They shed excess spin so the star can safely keep growing, rather than tearing itself apart from pure speed. Our own sun sits perfectly in the center of this story, offering me a familiar anchor with incredible scientific detail. Our sun definitely spins, but far slower than the chaotic young stars. I map its structured magnetic cycle. Its steady solar wind constantly carries both mass and spinning energy deep into the void. Over billions of years, that wind has quietly helped to slow our sun's rotation. The sun's swirling equator fuels its massive magnetic engine. That engine then shapes the wind, beautifully closing the loop between rotation and braking. Panning my telescope across the galaxy, I see this entire spectrum, from the violently fast, fiery infants down to the quiet, slow-turning ancient stars. This pattern tells me magnetic braking is far from a rare fringe effect. It is a main evolutionary force for stars. Spin also heavily dictates their physical shape and daily behavior. The fastest spinning stars actually flatten out, bulging significantly at their equators. That severe distortion warps their surface temperature. I've measured rapid rotators with blazing hot poles and strangely cool equators just from the strange gravity and pressure balance. That spinning motion also churns the star's guts, dragging fresh hydrogen fuel straight into the nuclear furnace and totally altering the star's lifespan. For extreme rotators, this deep mixing completely alters their lifespans and chemical outputs. Spin isn't just a quirky feature on the surface. It rewrites the entire biography of a star from birth to death. In tight binary systems, gravity tides join magnetic braking as a massive second influence. Those heavy tides lock the stars so their spinning matches their orbit. Then, magnetic winds steal that spinning energy, causing the two massive suns to spiral terrifyingly close together. This unseen interplay sparks a beautifully complex evolution. So we find our final theme. Spinning momentum constantly flows, and stars only evolve because those unseen pathways exist. Let's explore a distinct part of our cosmic story together. Earlier we looked at planets' disks and the slow reshaping power of gravity's tides. Now my focus shifts to plasma fields and stellar winds. In this different physics regime, magnetic forces matter just as much as gravity. As an astronomer, I see stars as giant magnetic machines. Their spin creates deep magnetic fields, which then regulate how they rotate. The universe's turning motion is not just about gravity. It is highly electrodynamic, written deep into the flow of charged particles and invisible fields. I find a quiet, peaceful reflection in all of this. A young star starts its life spinning fast and restless, blazing with wild activity. Then it gradually learns a calmer pace, shedding its rapid momentum out into the vast, quiet space around it. It reminds me that celestial change can be lawful and incredibly gentle, shaping motion without violence. Tonight, if your own mind feels like it is spinning much too fast, you can borrow this cosmic lesson. Let the stellar winds carry that energy away, and allow your racing thoughts to slow into a steadier, much softer orbit. Chapter 9, Galaxies and Dark Matter, the largest rotations in astrophysics. When I first learned that entire galaxies spin, it felt like a massive exaggeration. A galaxy is definitely not a solid object. It is a vast collection of stars, dust, and invisible mass, stretched across distances so immense that light itself takes forever to cross them. Yet through my telescope, I see a coherent turning pattern. It is a graceful choreography where billions of glowing stars circle one common center. Rotation on this massive scale is never a detail. It is a defining feature of deep space structure. It tells me how galaxies formed, how they evolved, and what kind of mysterious matter dominates their mass. Our most familiar example is the beautiful spiral galaxy. Spirals have thin disks where stars orbit in the same plane. Their bright luminous arms trace regions where deep space gas compresses and where beautiful new star formation stays highly active. These arms are not rigid painted structures spinning like a pinwheel. I prefer to think of them as fluid patterns, created by dense waves moving slowly through all that orbiting cosmic material. The massive underlying disk, however, is undoubtedly rotating. I can measure that stellar motion directly. By studying the delicate spectrum of starlight and gas from different parts of a galaxy, my colleagues and I can easily detect Doppler shifts. Light from the side spinning toward my lens shifts one way, while light from the side rotating away shifts firmly into the opposite direction. Using these shifts, I calculate a rotation curve. It shows exactly how orbital speed changes as we look farther from the deep galactic core. At first glance, this kind of calculation seems perfectly straightforward. In a simple model where most mass sits packed inside that intensely bright central region, I would expect speeds to rise near the core, then slowly fall farther out. Gravity should naturally weaken as you move away from the main bulk of the visible mass. This is exactly what happens in concentrated systems, like planets peacefully orbiting around their host star. But spiral galaxies do something entirely unexpected. My observations show that in many disk galaxies, orbital speed does not drop the way it should based entirely on the glowing visible matter. Instead, after rising near the center, those speeds stay surprisingly flat far out into the deep cosmic disk, even where the starlight fades to almost nothing. Stick with me here because this is a massive clue for modern astrophysics. These flat rotation curves tell me that mass keeps increasing with radius, way past the boundaries where most of the glowing luminous matter actually lives. Put simply, I am measuring extra gravitational pull from a massive source that does not shine or emit light the way normal stars and gas do. This invisible something is what we call dark matter. It is mass that interacts through gravity but stays totally dark. Now, my evidence for this material does not rely on rotation curves alone. But measuring galaxy rotation remains one of the clearest, most intuitive clues we have. It connects directly to physical motion that I can measure through a telescope and compare against standard gravitational rules. To see why this flat data points to hidden mass, imagine yourself floating out in a cold galaxy's outer disk. If the mass enclosed inside your orbit stayed constant as you drifted outward, gravity would fade away and your orbital speed would slowly drop. But to keep your speed constant, the dark mass enclosed within your enormous orbit must steadily grow as that orbital radius gets larger and larger. This does not mean the material's density remains highly packed. Density can easily drop with distance, yet the total enclosed mass keeps rising. That is exactly the mathematical result we get when a galaxy sits deeply embedded inside a giant, extended halo of heavy dark matter. This invisible halo dominates the mass budget at the outer edges, keeping orbital speeds high even where the starlight fades to black. So you and I can see dark matter doing two jobs. First, it acts like cosmic glue, holding those spinning stars together. Second, it carves out a massive invisible sinkhole that pulls in regular matter during formation. Our best observations suggest dark matter clumped up long before normal matter, collapsing under gravity to form massive invisible halos. Hot, regular matter eventually cooled down, sinking into these dark halos to build spinning galactic disks whenever the conditions were right. Through our telescopes, we only see that glowing disk, but it rests inside a giant unseen shell. But why do these massive galaxies spin? The whole universe wasn't just spinning at the start. Our current models show that newborn galaxies pick up their spin from massive gravitational pulls as they form. As gas clouds expand inside the cosmic web, they are never perfectly round or completely left alone. Nearby heavy clusters yank on them. Those tidal pulls create a twisting force, spinning up the newborn galaxy, while the larger universe keeps everything perfectly balanced. Over millions of years, this steady twisting gives the gas a spin. When all that material finally settles down, that gathered momentum becomes the engine driving galactic rotation. But when normal matter falls into a dark halo, it acts nothing like the dark matter around it. We believe dark matter is practically ghost-like. Its particles just pass through each other without losing energy like normal gas clouds do. Regular matter, though, can easily burn off its extra energy. Gas particles smash together, heat up, cool down, and glow into space. As that gas cools but keeps spinning, it flattens into a beautiful disk. It is like watching a spinning solar system form, just on a cosmic scale. A flat disk perfectly lets the gas pack tightly together while obeying the physical laws of that gathered spin. Eventually, stars ignite inside the disk, moving right along with that spin. It becomes a swirling stellar island inside a dark halo, but as you might guess, not every galaxy looks like a flat disk. Many we photograph are huge, round ellipticals, where stars buzz around in chaotic swarms instead of gliding in one flat plane. They still slowly rotate, but random, messy stellar orbits completely overpower the calm, ordered spin. One major reason we see this difference is galactic collisions. When two galaxies crash together, all those neat, flat orbits get violently scrambled. The original spinning energy turns into random, chaotic motion, inflating the whole system into a giant stellar sphere. If there is gas left, it might cool and build a new disk, but when dry galaxies crash, they leave behind a round elliptical where spin is hidden. That original spin never dies, it simply shatters into millions of different stellar paths. Watching a galaxy spin tells us exactly where its unseen mass is hiding. Near the glowing center, normal matter provides the strongest pull, especially if the galaxy has a bright, packed core. In these tight zones, those measured rotation speeds spike dramatically. But as we look toward the edges, dark matter takes over, completely flattening the curve. Every galaxy we observe has a unique spin profile, letting us map out exactly where the dark and normal matter ended up. As astronomers, we study thousands of these curves, using them to ruthlessly test our best theories of how galaxies actually form. But our evidence for the dark goes way beyond spinning disks. Entire galaxy clusters move far too fast for the amount of light they emit. We also watch invisible mass bend starlight like a giant lens, proving there is far more out there than just glowing gas. Even the ancient microwave background of the universe shows us a cosmos built primarily out of heavy, invisible stuff. Those flat spin curves perfectly match our broader observations. The stars simply move like they are trapped inside massive, invisible ghost halos. Still, studying these spinning galaxies has sparked some wild alternative theories over time. Some colleagues suggest tweaking the laws of gravity at vast distances to explain the spinning without needing dark matter at all. Those models actually predict some galactic shapes quite well, and they still trigger heated debates at our observatories today. However, the massive mountain of cosmic data, from bending light to deep space surveys, still leaves most of us confident in dark matter. You and I are watching a living scientific mystery unfold, so we must be incredibly careful. In my field, galaxy rotation sets strict limits. Any new theory must match the cosmic dynamics we observe across countless distant star systems. Through my telescope, this galactic spin also carves out some of the most beautiful, striking structures in our universe. The gorgeous spiral arms, bars, and rings I map out are simply how a spinning cosmic disk reacts to gravity, internal tremors, and galactic collisions. I often watch rotating disks form central bars. These stretched shapes shift angular momentum through the galaxy and funnel fresh gas straight toward the core, often sparking central star birth or quietly feeding a supermassive black hole. I see spiral patterns acting like gentle traffic jams, squeezing cosmic gas and sparking new star birth as stellar material drifts through. Galactic warps usually catch my eye when dwarf companions collide, or when the visible disk misaligns with its massive dark matter halo. These stellar features run deep. To me, they are the visible, glowing language of a spinning gravitational system. Deep in the core of most galaxies I study, including our Milky Way, sit quiet, supermassive black holes. The link between galactic spin and these central black holes is quite complex. Yet I know this stellar spin ultimately helps funnel gas inward. Gas has to shed angular momentum to reach the core. The bars, spirals, and galactic collisions I track create perfect pathways for this drop. Even in the dark, physics persists. Let's look closer to home. Cosmic collapse demands angular momentum shift and spin shapes that flow right here in our Milky Way. Our sun slowly orbits the galactic center, and that gentle journey is just one small piece of the Milky Way's grand, sweeping rotation. I map our local disk, finding stars locked in a smooth, unified spin, while the outer halo holds ancient stars drifting in chaotic, random paths. My measurements of star speeds, spinning gas clouds, and dancing dwarf galaxies all help me calculate the Milky Way's true mass, revealing the vast, hidden shape of our dark matter halo. Looking up from the observatory, our night sky is just a local window from inside a spinning system, completely ruled by unseen gravitational ghosts. What strikes me most about galactic rotation is the deeply vast time scale. A single distant star I track might take hundreds of millions of years just to finish one slow, peaceful lap around the galactic core. Still, the rhythm remains so steady that galaxies keep spinning smoothly for billions of years, only breaking their stride during massive cosmic collisions. This rotation is not just common, it is beautifully persistent. It acts like an ancient memory of how primordial dust gathered, holding the spin from the early cosmic web. Let me add a final piece to the story we are building today. We have already traced spin from giant clouds to planetary disks, observing how deep gravity tides and magnetic solar winds slowly reshape that motion. Now I look at rotation within the absolute grandest stable structures my telescopes observe. Vast galaxies where glowing, drifting stars actually expose the heavy presence of invisible dark matter. The familiar physics of gravity and momentum hold true, but the stage grows. For us, rotation becomes a tool to weigh the cosmos, offering a deeply humbling perspective. When I photograph a distant galaxy, the starlight is just a fraction of its true binding force. But by carefully tracking the sweeping motion of its stars, I can decode the rest. Right now, you're resting on a spinning rock, orbiting a spinning star, adrift in a spinning galaxy, tucked inside an unimaginably vast cosmic web. If that immense scale feels overwhelming, let it soothe you instead. It reminds us that our tiny place here is cradled by deep, ancient, predictable rhythms. And for tonight, it is enough to simply rest deeply inside those quiet rhythms. Chapter 10, The Ultimate Mystery. Is this spin a fundamental law or just an echoing memory? After tracking this motion from nebulas to planetary disks, and from bright galaxies out to dark matter halos, a profound question always haunts my nights. Is our entire universe a spinning place at its very core, as if rotation is woven into the fabric of reality? Or is this cosmic spin just the natural result of mixing gravity, messy asymmetry, and endless time? A lingering ghost of the Big Bang, surviving only because momentum is perfectly conserved, and the empty void offers no quick way to stop it. To tackle this mystery properly, I have to split the concept of fundamental into two meanings. The first is global. Does the entire cosmos slowly rotate as a single massive entity, pointing to one true axis or an overarching, universal spin? The second meaning is purely local. Is spin simply unavoidable in forming galaxies because of raw physical laws like conservation, even if the wider universe itself sits perfectly still? They sound quite similar, but in my field, they demand entirely different cosmic evidence and yield vastly different conclusions. I start with the global question because it is easily the most dramatic mystery. If the entire universe rotated together, it might leave subtle signatures in my data. A universal spin would actually warp the cosmic microwave background, baking a giant swirl or a tilted axis into the oldest light my satellites can measure. You and I might wonder if cosmic rotation shapes the largest structures out there. It could align distant galaxies, or give those beautiful spiral patterns a shared spin across our sky. In pure theory, a spinning universe could leave faint fingerprints on the ancient light my instruments capture, altering that deep cosmic background. But what do our observatories actually see? Modern astrophysics tells us that on the grandest scales, the cosmos looks incredibly uniform. I know it is not completely smooth everywhere, but my colleagues and I see no real proof of a preferred direction. A massive, spinning universe would leave an obvious trail. The fading afterglow of the Big Bang is incredibly smooth, and those tiny thermal ripples match perfectly with a deep space environment that simply does not spin as a whole. We astronomers have combed the data for any hidden twists or large-scale vorticity in the void. So far, the limits are strict. If the entire cosmos is turning, it is vastly slower than cosmic expansion. it is far too weak to trigger the swirling planets, stars, and galactic disks we photograph every single night. That is a vital piece of astrophysics to hold on to tonight. Space itself does not need to spin for localized celestial bodies to pirouette. The spinning worlds in my telescope are not trapped inside some giant cosmic whirlpool turning everything in lockstep. Actually, one of the most beautiful things we observe is that orbital directions are entirely mixed up. Worlds within a single solar system generally spin together, simply because they collapsed from the exact same dusty stellar nursery. But panning across the heavens, galaxies tilt every which way. A universal spin would have to be incredibly gentle to let these local histories unfold. And our finest observational data proves it is a microscopic factor at best. Let's think about this together. If spin is not forced upon the cosmos, why is it everywhere? This is where physics gets truly profound. Turning might just be the natural, expected fate of how dark matter and gas evolve under the gentle grip of gravity. Our deep universe started with tiny flaws, not perfect stillness. Gravity grabbed those tiny ripples, pulling free matter into massive, drifting clusters. During that long cosmic dawn, the slightest sideways drifts and uneven clumps were locked in and magnified. The strict laws of physics, specifically the conservation of angular momentum, made those primordial sideways glides almost impossible to stop. As cosmic gas cooled down and lost energy, it relaxed into spinning halos. The result is a night sky full of spirals, not from a grand command, but because spinning is the most natural surviving rhythm for building galaxies. Through my lens, a spin is a memory, a living record of how ancient stardust flowed, collided, and found peace. Calling it memory is not mere poetry. It is a mathematical truth about what nature preserves. When a new star system is born, it inherits the swirling momentum of its birthplace. Over eons, that momentum shifts through gravitational tides, magnetic stellar winds, and deep space collisions. But unless pushed away, it stays. A planet's day and tilt whisper secrets of ancient impacts and long tidal histories. A star's gentle spin tells me about its dusty birth cloud and its slow magnetic breaking. A whole galaxy's rotation reveals the deep gravitational pulls of the cosmic web and the violent mergers that built it. That spin survives simply because the universe aggressively conserves it, and the cosmic breaks take billions of years to work. But there is an even deeper layer to this concept, hiding in the very bedrock of physics. The conservation of that spin is directly woven into the beautiful, endless symmetry of empty space. Because the rules of astrophysics do not change when I turn my telescope around, nature guarantees a preserved momentum for that turning motion. This elegant link is no random accident. It forms the very spine of astrophysics. The cosmos does not favor spinning out of some strange emotional desire. Rather, the void is crafted with a quiet symmetry, ensuring that momentum stays perfectly protected in the lonely dark. Seen through that lens, spinning is absolutely no mistake. The rigid rules of its survival are permanently etched into the grand laws of spacetime. So what do you and I learn? Conservation alone does not force every star to spin fast. A celestial body might hold very little momentum, or hide it in complex orbital dances that never look like one simple, clean spin. Through my telescopes, I see galaxies ruled by random starlight instead of smooth spins. Tides slow some planets down. I watch some stars shed their spin through heavy solar winds, yet the angular momentum never truly vanishes. It simply shifts into new orbits, blown off gas, or out into the cold surrounding void. This proves rotation acts like a cosmic memory. The spin just changes form or hiding place, so the question we astronomers ask gets sharper. If rotation is a memory, what gave the universe that very first twist we see today? Here you and I reach the edge of settled science and enter the unknown I study. My colleagues and I know the early universe held tiny ripples of heat and cosmic matter. We see strong proof that gravity and tidal pulls spin up young star clusters and dark halos. But exactly how that spin flows across the galaxy and sets during formation keeps me awake at night looking at the data. My computer models show massive dark halos spinning up from cosmic crashes, while our telescope data keeps those theories grounded. But we are still writing this story. Out in the deep dark, I observe places where spin and the actual fabric of spacetime bend together directly. Einstein taught us that a spinning mass actually drags the fabric of space along with it. We call this frame dragging, and trust me, it is no metaphor. We have measured it right over Earth, and I look for it near extreme, rapidly spinning neutron stars and black holes. The shape of space allows for truly remarkable things. Like zones where you would be physically forced to move along with a black hole spinning. Near these monsters, rotation is not simply moving through empty space. It shapes the very geometry of space. This does not mean our whole universe spins, but it proves to me that rotation holds a deep physical truth, far beyond the simple idea of a spinning ball. Black holes bring this cosmic memory into sharp focus. I can describe one entirely just by its mass and its spin. That spin acts as a fossil record of exactly how it first formed. Whether it slowly ate gas from a disk or crashed into another dead star, absorbing all of that swirling energy. Astronomers like me measure these spins by watching glowing matter rings and bright energy bursts. So you see, even the darkest pockets of the void carry the lasting, twisting fingerprint of rotation. Let's look at this honestly together. Despite everything, rotation is never some mysterious, magic force pushed into reality from outside. It is simply what I expect when I look at a cosmos that is not perfectly smooth, paired with strict laws of physics and gravity pulling clouds of gas together. Things spin all over the sky because perfect balance is rare. Gravity magnifies tiny motions, and the universe has almost no fast way to erase that turning energy. This shows me what the cosmos actually prefers, if we can say that. It prefers pure, quiet consistency. It loves physical laws that stay the same no matter where I point my lens. It prefers rules that keep energy honest. Under those rules, history is everything. We never needed a giant, universe-sized spin to start with. Space just needed a tiny, bumpy irregularity, and billions of years of time did the rest. There is one last cosmic truth I want to share, so we do not oversimplify things. Spin is not just a dusty memory of the Big Bang. It actively shapes the sky right now. It holds solar disks steady, molds young stars, pushes gas, and drives massive magnetic fields. It invites tides to pull, winds to blow, and dead stars to collide. Through my eyes, rotation is both the result and the reason. Born from old physics, it survives the cold to dictate what a galaxy will do tomorrow. When I look at it, spin is simply the universe unfolding naturally. It is not an extra spice, but the main plot. Stepping back from my data, it turns into something quietly beautiful. Our cosmos does not need to spin as a whole, just to be filled with turning worlds. It only demands that nothing starts perfectly smooth, and physics refuses to let those little twists fade away. You and I can see rotation is just the universe keeping its receipts, a gently comforting thought. Even our own human lives are full of motions that seem totally chaotic when viewed up close. Looking through the lens, I see how tiny beginnings lock into stable, ancient orbits. You're part of a cosmos that remembers. Let that steady cosmic gravity anchor you tonight. Just feel your thoughts slow down as your long day finally turns quiet. Still awake, I've got another stargazing session lined up for us. Just one more gentle journey through astrophysics that you can simply drift off to. But if sleep is already pulling you into orbit, let it. Thanks for spending this quiet watch with me, my friend. Sweet dreams among the galaxies. I'll see you next time the sky is clear.